Hello everyone, I'm Yannick Sirineni, finally a computer science undergrad, and I work at the Agents and Applied Robotics Group at the International Institute of Information Technology in Hyderabad, India. I really wished for an in-person conference, but my compliments to the conference organizers for doing a great job in making the conference online and giving us an opportunity to present virtually. In this video, we present our paper titled Decentralized Collision Avoidance and Motion Planning for Multi-Robot Deformable Payload Transport Systems. The primary goal of this paper is to address collision avoidance and motion planning of multi-robot payload transport systems carrying deformable payloads. Each payload transport system, or PTS, is constrained to navigate safely in an environment having other decision-making formations and static obstacles. So this has applications in various industries and warehouses for transporting deformable payloads. Essentially, we are looking forward to cases where the formations squeeze in through tight and narrow spaces by deforming themselves as shown in the figure. Here, the two formations initially deform themselves so that they can enter a narrow corridor. They again deform themselves even more so that they can cross past each other. Once they cross each other, they start expanding to their original sizes. So a payload transport system, or PTS, is a formation of loosely coupled non-holonomic robots that cooperatively transports deformable payloads. Each PTS consists of one leader and multiple followers, and the followers maintain a desired relative position with respect to the leader. In this presentation, we use the terms PTS and formation interchangeably. So each formation is defined by the number of robots in the formation, Rmax, which denotes the radius of the payload in the undeformed state, Rmin, which denotes the radius of the payload in fully deformed state. So these are derived by considering the deformability constraints of the payload being carried. In this paper, we model each formation as a circle where we deform and expand the circle. This picture shows a few of the various shapes and configurations of a formation. Real-time collision avoidance for such systems is challenging due to the fact that A, we have to exploit the deformability of formations, B, high-dimensional configuration space of multiple formations, C, non-convexities in workspaces, and D, heterogeneities in the type of formation, as in the formation can vary in the number of robots, size, and deformability constraints. Moreover, existing solutions for navigation do not consider heterogeneous multi-formation collision avoidance. We resolve the above challenges by embedding workspaces defined by a multi-robot collision avoidance algorithm and multi-scale repulsive potential fields as constraints within a decentralized convex optimization problem. Specifically, we present two main steps to plan the motion of each formation. First, we compute collision-free multi-scale convex workspaces over a planning horizon using a combination of ORCA and repulsive potential fields. Subsequently, we compute the motion plans of formation over a horizon by proposing a novel formulation for collision avoidance, and we leverage a model predictive controller, or MPC, to solve the problem. We present the potential field formation ORCA-MPC algorithm, or PF-FORCA-MPC in short, which is decentralized, and there are primarily 6 stages, namely global path planning, computing artificial repulsive potential fields, radius over the horizon, computing ORCA constraints over the horizon, model predictive controller, and finally the formation controller. The first step is global path planning. So initially, the leader of each formation computes a collision-free path from its source to destination by considering static obstacles in the environment. We then do cubic spline interpolation to get multiple waypoints in the path. At any time instant, the preferred position of a formation is the closest waypoint in the interpolated path, and the preferred velocity is a vector pointing towards the preferred position from the current position with a magnitude of maximum speed, and is given in this expression. Any global path planner can be used for this purpose, and we have used the RRT star algorithm for our implementation. So the next step is local path planning. At every time instant, we plan the motion of formation over a fixed time horizon and take an action for the current time step. Essentially, we look at k steps ahead into the future and choose a control input only for the present time instant. So we present a novel formulation of a model predictive controller, or MPC, to compute the leader's locally optimum control input. The objective of this MPC is to minimize the deviation of the current velocity with the preferred velocity, and also minimize the deviation of the preferred position with the current position. The MPC is constrained by A. Linear translational dynamics of the leader, B. Collision avoidance constraints on the velocity. So the velocity at the kth step of the horizon has to lie in this convex region ORCA of k, which guarantees collision avoidance. And the remaining constraints are positional and velocity bounds on the formation. The output of this MPC is the trajectory and control inputs over the planning horizon. And finally, the formations share their predicted trajectories with other formations. So our task is to construct this convex region ORCA of k for each step k of the horizon. For this, we use artificial repulsive potential fields. The core idea of this is to compute an artificial potential acting on a formation over the horizon due to the presence of obstacles, and based on this, we deform the formation so that it can navigate through narrow and tight spaces. The repulsive potential on a formation with respect to obstacle I is given by this expression. So the magnitude of the potential field increases hyperbolically with a decrease in distance. So if the distance between the formations is less than a lower bound L, then a maximum potential field P max acts on the formation. And if the distance is greater than an upper bound U, then there is no influence of potential field on the formation. So L denotes the lower bound on influence of the potential field and is given by this expression. So when the formations have deformed to their maximum extents and are just touching each other or are just beside each other, so a maximum repulsive potential of P max acts on the formation. So, and U denotes the upper bound on influence of the potential field and is given by this expression. The last term in the equation defines the normalized velocity deviation from the preferred velocity. When the normalized velocity deviation is high, it implies that the formations are nearly static and have deviated from their preferred velocities due to the presence of other formations and obstacles. So this leads to an increase in the potential field region of influence, which in turn leads to the deformation of formation. So this deformation over the horizon squeezes the robot workspace and enables the planner to look ahead for feasible trajectories. So the total repulsive potential field acting on a formation due to all the obstacles is a vector sum of individual potential fields. Here Pi is the magnitude of the potential and beta is a vector of the potential and is a vector pointing away from the formation. The total potential field is clamped to a value P max, which denotes the maximum deformation a payload can withstand in one time step. So this is specific to the payload being carried. The next step is computing radius over the horizon. So we deform the formation over the horizon by decreasing its radius using the magnitude of repulsive potential field acting on it. Decreasing the radius reduces the region of influence of potential field, which in turn enables the formation to navigate through narrow and tight spaces. The deformation in radius is applied over the horizon, and this deformation rate is directly proportional to the potential field acting on it. Since it's essential for the payload to get back to its original size, we include a small expansion potential field which increases the radius of the formation. The next step is computing ORCA constraints over the horizon. We compute collision avoidance constraints on the velocity for each step of the horizon using the computed radius of formations and the received trajectories over the horizon of the neighboring formations. So each formation constructs ORCA subscript I with respect to all the neighboring formations I for each step of the horizon, where ORCA subscript I refers to the collision avoidance constraints on the velocity with respect to formation I, and this is constructed using the optimal reciprocal collision avoidance algorithm, also known as ORCA. So the set of collision avoidance velocity at the kth step of the horizon is the intersection of constraints with respect to all the neighboring formations. So this expression is used as a constraint in the MPC formulation. It's important to note that the ORCA of k is a function of radius of all the formations at the kth step of the horizon. So the final step is the leader-follower formation control. The output of the MPC is the holonomic control inputs over the horizon,
we map the holonomic control input of the first step of the horizon to non-holonomic control inputs U and omega. So these are the control inputs of the leader of formation. We then incorporate a decentralized, bio-inspired, neurodynamic-based leader-follower approach for computing the control inputs of followers using the leader's control inputs and state. The desired distance of each follower with respect to the leader is the radius of the formation at that instant. So in cluttered and dense environments, MPC might fail to find feasible solutions. So there are two cases. Case 1. The half planes corresponding to ORCA constraints of the first step of the horizon, that is k is equal to 1, do not have a common region. In this case, we solve a 3-dimensional linear program to find the control input only for the present time instant. Essentially, we choose the safest possible velocity that deviates the least from ORCA constraints. Case 2 is the half planes corresponding to ORCA constraints of some step k greater than 1 do not have a common region. In this case, we solve a quadratic program to compute control input only for the present time instant. So this formulation is similar to our MPC formulation. We then compute the predicted states over the horizon by assuming that the formation traverses with uniform velocity throughout the planning horizon. The algorithm is validated using several simulation environments, and in this video we showcase 4 simulations. In this simulation, we compare the performance of PF-FORCA-MPC presented in this paper with our previous work FORCA algorithm, which is a reactive collision avoidance algorithm which does not do any predictive planning. Also, FORCA only considers rigid payloads. So in the simulation, we consider all the formations to be rigid so that we can compare the algorithms better. The point A in the plots refers to the time instant when the red formation deviates from its desired path to avoid a collision, and point B denotes the time instant when the red formation returns to its desired path after avoiding a collision. So the leader-follower distance between points A and B with FORCA has sudden fluctuations as the formation takes a sharp turn to avoid a collision, whereas the leader-follower distance with PF-FORCA-MPC is quite stable without any sudden fluctuations as it does predictive planning. Similarly, if you look at the velocity plot, the velocities of the robots between points A and B with FORCA have sudden jumps while avoiding a collision, whereas that with PF-FORCA-MPC, the velocities are much more stable without any sudden jumps. Through this simulation, our solution shows the ability of formations to look way ahead into the future and take their present action, hence avoiding any sudden jumps in their velocities and trajectories. Narrow corridor simulation. In this simulation, we consider a narrow corridor scenario where there are 2 deformable payload transport systems which move to the opposite sides of their corners. And this is simulated in the gazebo simulator. At this point, the formations deviate from their desired paths, which increases the region of influence of potential field, and the formations deform themselves to squeeze through the narrow spaces. Once they cross each other, they start expanding to their original sizes. Antipodal simulation. In this simulation, we consider 16 formations where each formation has unique deformability limits and each formation has different number of followers. The formations are located uniformly on a circle, and the formations at antipodal positions are expected to swap positions with each other. In dense cases, the formations deform themselves so that they can squeeze in through the narrow spaces. Later, they start expanding themselves and get back to their original sizes. Since the algorithm is decentralized, it scales well with the increase in number of formations. Finally, a real robot experiment. To demonstrate the proof of concept of our algorithm in the real world, we use 3 custom-built non-holonomic differential drive robots to move in a formation while transporting a virtual deformable payload. The radius of the payload in undeformed state is 1.4 meters and can deform up to a radius of 0.6 meters. Artificial repulsive potential fields acts on the formation when it approaches the narrow corridor. As a result, the formation deforms itself so that it can pass through the narrow corridor. Thank you. This concludes our presentation.